Okay, back again. Another couple of topics which I think are very short topics, and we can cut them down quite a lot. The first one here is called electrical appliances. Now appliances, here's an electrical appliance, here's a hand blender, that's my electrical appliance, and there's the radio at my kitchen, that's an electrical appliance. An electrical appliance is anything that runs off electricity that you use for something. Now they all transfer energy. Electrical energy is very useful. It's not an energy store, but it's a very useful way of getting energy in and out of houses and factories. In the past, we used to run our houses on gas. I live in an old Victorian house, and there are some gas pipes still in the walls from when electricity wasn't readily available, and you would light your house through gas. But with electricity it's very easy, because you just have some wires coming in the house bringing lots of energy in, and all your electrical appliances can transfer it into the types of energy that you need. So if we look at my hand blender here, that runs off of electrical energy, and that is generated in one of a number of ways. But then this is built and designed to transfer that electrical energy into kinetic energy, because it spins around and it blends up food. So that's the useful energy, the kinetic energy of this thing going round, but it also makes quite a noise while it's doing that, and it also gets hot. So like all appliances, anything that transfers energy, it is not 100% efficient. Some of the energy is wasted. So in here, the useful energy is the kinetic energy of this thing going round. The wasted energy is the thermal energy of the motor getting hot, and the sound energy of the noise that it makes while it's going on. My radio here, that is designed to transfer electrical energy into sound energy. If it was a television, it would turn it into sound energy and light energy as well, because you've got a picture coming out. But also this thing gets warm, and so some of the energy that goes in is turned into thermal energy. And that is electrical appliances. They will ask you about a number of electrical appliances and say what type of energy is it designed to transfer, and what kind of energy would be wasted from it. And I think we can use quite a bit of common sense to work those out. So that's done. That's that done. The next thing is all about electrical power. Now the power lead on this blender is thicker than the power lead for my radio, and that is because this thing runs off, it needs more energy every second to make it run than my radio does. And if you look at the power lead on a kettle or a toaster, they use an awful lot more energy every second, and so they've got fatter leads on there so that you can get more electrical energy down there every second to run these things. So the power of something is how quickly it transfers energy. I usually say how quickly it uses energy, but we're not using it up, we're just taking it from one form to another. And all of these things have a power rating on them in something called watts. So if we look at this one here, you can see it runs off 220 to 240 volts. That's the mains electricity, and underneath it, it says 200 W. So this uses 200 watts, which basically means it uses 200 joules of energy every second. And if we look at my radio here, which is the right way up, a bit dirty on the bottom there, but that says 5 watts, power consumption 5 watts on there. So obviously the radio uses much less energy per second than the blender does. And when you pay for your electricity bill, you're basically paying for how many joules you've used, and they need to know which appliances were turned on and how long they were turned on for. So you need to know that power is measured in watts, and that to calculate the power of something, you need to know how much energy it has transferred and how long it was on for, how many seconds, and that's how you calculate the power. So an exam question would say something uses 100 joules of energy in 5 seconds, what is the power rating? And you say, okay, well, it's 100 joules in 5 seconds, 100 divided by 5, that is 20 watts. So that appliance uses 20 watts. Now, as with all of these things, you'll have realized by now there's equations to remember and things to remember. And so for this one, we say kilowatts, megawatts. Watts is power. Divide energy by time in seconds, not hours. So they will trick you in the exam, and they will give you something in kilowatts. and you have to go, hang on, that's not right, this should be in watts, because that's the standard unit. So if they give you 3 kilowatts, you would say, okay, kilo means 1,000, so that's 3,000 watts. And they say, how much energy is it used if it's turned on for a minute? And again, you say, okay, we're supposed to be measuring this in seconds, not in minutes, so I'll divide that by 60 to do that. So kilowatts, megawatts, watts is power, divide energy by time in seconds, not hours. Don't let them trick you for that one. So that's just an equation you need to know. And there's lots of examples that you can do in the lovely book here, which you have access to on Caboodle. And the other thing you need to know is that efficiency is how much of the useful power, of how much of the total power that you put in is turned into something useful. Now, you would have seen in the last lesson that we looked at efficiency of energy. So if you put 100 joules of energy in and you get 800 useful joules out, then that's 80% efficient. But it's the same with power, because power is just how quickly you're using up that energy. So as I said last time, efficiency, it's good stuff out over total put in. Energy or power, it's all the same thing. And I really think that is it. We are rattling through this stuff. So that's it for energy, types of energy, the way that energy is transferred from one form of energy into another. We've done a few equations about how to calculate power, how to calculate efficiency. We've learnt about kinetic energy, which is how to calculate that, which is half of the mass times by the velocity squared. Kinetic energy will move me with half an m and a v times v. We also learnt that gravitational potential energy can be found. You multiply the weight by the height above ground, and that gravitational energy turns into kinetic energy when things fall. So if you know the gravitational energy, you can work out the kinetic energy by the time it gets to the bottom. We spoke about weight, and we said that weight is the force at which your mass is pulled down because of gravity. And if you go to the moon, your weight changes, but your mass doesn't. It's just not pulled down so hard with gravity. So we said mass times gravity makes your weight in newtons, get your units straight. But that's it. Next time we're going to start looking at renewable and non-renewable energy forms and energy sources and how we get our energy. So that's it for me. I'll see you next time.